In this video, we will discuss reactions that proceed by radical pathways. The learning goals for today are to draw the complete curved arrow mechanisms for reactions that proceed via these radical pathways. These curved arrow mechanisms will differ from previous mechanisms learned, as those mechanisms proceeded via heterolytic bond cleavage, by which two electrons move together in the same direction, represented by these double-headed arrows, versus homolytic bond cleavage, in which single electron movement occurs, represented by these single-headed arrows or single barbed arrows. All the reactions that we have discussed up until now do proceed via heterolytic bond cleavage. At least they do if we learn the mechanism. For some of the reactions where I said we won't learn the mechanism for this, perhaps the reason was it proceeded via homolytic bond cleavage, which we will discuss today. So single electron chemistry. Those mechanisms can be described by three steps: initiation, propagation, and termination steps. So we will learn those elementary steps. For reactions where the electrons move as pairs, we've discussed elementary steps such as coordination, heterolysis, electrophile addition, nucleophile addition, etc. Today, we'll learn new elementary steps for reactions where the electrons move as single electrons. Then we will explain the regioselectivity of radical reactions, so reactions that proceed via radical pathways. And all that means is that two constitutional isomers or more than one constitutional isomer could be formed, but one is favored. We will predict the products of reactions that proceed via radical mechanisms and then explain the relative stabilities of radical species based on substitution pattern and delocalization, aka we're going to draw resonance structures. That should be really fun when single electrons are involved. All right, we'll make some analogies to carbocations to achieve this learning goal. Now, before we even get started on this process, let's pause and propose reagents for each of these transformations. Just do your best, pause, give that a shot. Once you've answered these questions, let's consider this question, which is, can I leave butter out on the counter? Can anyone leave butter out on the counter? Is that a good idea? I like to have soft butter to put on my bread, so can I leave it out on the counter? Okay, confession time. I did leave it out on the counter and now it tastes funny. What happened? If you think you know, write it down. So we've done three things. We've predicted reagents for these transformations. We have thought about whether or not we can leave out butter on the counter. Oops, I did it. Now it tastes funny. What happened? And once you've written down your thoughts on that, one more question for you. Quick, don't think. So when I say free radical, what are the first words that come to mind? Write those down. This is a lot more fun in person. Well, have a chuckle at whatever you wrote down here. And then let's get started. So we have several reactions we're learning today. We'll come back to this reaction chart and summarize each of these reactions. For now, let's consider a reaction we have encountered in the past and pretty far in the past. And that is hydrohalogenation of alkenes. When an alkene is treated with HX, in this case, X is bromine, those two atoms, H and X, H and bromine, add across the two carbons of the alkene. Two constitutional isomers of the alkyl halide product are possible. Hydrogen could add in this fashion and bromine to the other carbon of the alkene, or vice versa. Bromine could add to the tertiary carbon and hydrogen to the other. Either a secondary alkyl bromide is formed or a tertiary alkyl bromide is formed. You may recall that the first elementary step in this process is an electrophile addition step, where the electrophile E plus is H plus. If the hydrogen atom adds to the more substituted carbon of the alkene, this carbocation intermediate would be formed. This species represents a secondary carbocation. The carbon that hydrogen did not bond to, this one is secondary. And as it is no longer bonding with these pi electrons, it has an unfilled octet and represents the stress on this molecule. On the other hand, if the hydrogen, the proton H+, had bonded to the less substituted carbon, this one, of the alkene, it would generate the following species that has a positive charge, a carbocation, on the tertiary carbon, the other carbon of the alkene, this one right here that the proton did not bond to. You should recall that tertiary carbocations are lower energy than secondary carbocations. Thus, this lower energy intermediate is correlated with a lower energy activation barrier, a lower energy transition state. Thus, the activation barrier to form that tertiary cation is lower than the activation barrier to form this secondary cation, that one, since it's higher energy. Thus, there is a faster rate of formation of the tertiary carbocation, and the observed product is derived from this intermediate. The first step is rate determining, but once that tertiary carbocation is formed, the second step can occur, which is a coordination step between the bromide anion and the carbocation. The same type of step would have formed the secondary alkyl halide, but since the tertiary alkyl halide is formed faster, the secondary is not observed. The product resulting from the secondary carbocation is also not observed. The major product of this reaction is the more substituted alkyl bromide resulting from the more substituted and more stable tertiary carbocation. This product is often called the Markovnikov product. I do hope that this was a helpful review. It's one thing to memorize or remember that the Markovnikov product is observed when alkenes are treated with HX. It's another thing to remember why. So please do keep in mind why. And keep in mind the overarching principle, which is that the product is formed via the lowest energy pathway. In my chicken scratch there, that's what that says. The Markovnikov product is observed via the lowest energy pathway, via the tertiary carbocation. Now that we have reviewed hydrohalogenation of alkenes via this heterolytic mechanism, right? Electrons are moving in two electron pairs as we're used to. Let me show you a really interesting observation. When this same transformation is carried out, but in the presence of peroxides, we're calling that the per in peroxide is referring to that oxygen-oxygen bond. When this transformation is carried out in the presence of peroxides, a different outcome is observed. In fact, what do we see? We see the secondary alkyl halide, which is present as a mixture of diastereoisomers. There are two stereocenters here. And not what we would have expected. I bet we would have expected the tertiary alkyl halide. And I know that we would have because we just spent several minutes discussing why tertiary product is formed. It was formed via the more stable tertiary carbocation. So the only difference is the presence of peroxides. And now magically, the other constitutional isomer, the anti-Markovnikov product, as we have referred to it previously, is formed. How can we understand this result, that the less substituted alkyl halide is formed, aka the anti-Markovnikov product? Well, what we can say for sure is that it's formed by a different mechanism. It's not formed by the same mechanism because the higher energy pathway will not be observed. That violates the laws of the universe, that violates the laws of thermodynamics. So there must be a different mechanism in the presence of peroxides. What might this alternate mechanism be? Yes, it's going to involve radicals. Who would have known from the title of today's lesson? Radical mechanisms have three types of steps: initiation, propagation, and termination. And I've described each of those steps below. Each type of step will involve homolytic bond cleavage or homolytic bond formation. Heterolytic electron movement involves two electrons moving in the same direction. At the beginning of the lesson, I showed you two pi electrons moving together. Heterolytic cleavage of this pi bond. Truly, I've just drawn two resonance structures, but that's okay. For homolytic cleavage of the pi bond, one electron moves to one carbon, the other electron moves to the other carbon, shown by those single barbed arrows, and voila, there we go, a diradical. Okay, truly these are resonance structures of one another. That's okay though. Like we can look at heterolytic and homolytic cleavage of sigma bonds. Heterolytic cleavage of this sigma bond, this is called a heterolysis step, would lead to a carbocation and a halide leaving group. Homolytic cleavage of this carbon-bromine bond would lead to a radical and a halogen, also a radical, so two radicals. Two electron movement, double-headed arrow, two electron movement. There are those two electrons. There are two electrons moving in the same direction. Versus one electron movement, homolytic cleavage, the electrons are moving in different directions. Let's work through this mechanism. Radicals must first be generated. So that happens in what is called an initiation step. A species with all paired electrons undergoes homolytic bond cleavage to form species with unpaired electrons. As you know, the oxygen-oxygen bond is weak, and as such, it can undergo homolytic bond cleavage to form two radical species, where the electrons that were in this bond are now localized on these two radical species. If you're wondering, wait, where do these come from? Well, I can assure you that this discovery was certainly an accident, as many of the best discoveries are. As you know, a common organic solvent is the ether, such as diethyl ether, where these R groups are ethyl. And a common contaminant in ether solvents are these peroxides that are derived from the ether itself. So likely the chemist who ran this reaction did not realize that there was a peroxide contaminant in their ether solvent and then just discovered this interesting pathway. So the peroxides came probably from the solvent. And really only trace amounts are necessary because this process is catalytic, as you will see. All right, and the initiation step, a species with all paired electrons, no radicals here, forms species with unpaired electrons, aka radicals. Cool. Now that the radical has been initiated, it can generate new radicals. In fact, the alkoxy radicals can react with HBr in the following manner. So a radical, that would be the alkoxy radical, just thinking about the definition of propagation, interacts with a closed shell species. What is that? A closed shell species just means that all the electrons are paired. That's what I was discussing up here. So all paired electrons, aka no radicals. So a radical interacts with not a radical to generate a new radical. And in this case, that new radical is the bromine radical. So one of the electrons from the HBr bond is now localized on bromine. The other electron is making this OH bond. So I don't know, we can try some more colors here. Everyone loves when I do that, right? All right, I apologize if you cannot tell the difference between these colors. My options are limited. Yeah, there we go. Okay. So this new radical can continue reacting, and in fact, the bromine radical will react with the pi bond of the alkene. Okay, the unpaired electron on bromine is now making a bond with one of the electrons from the pi bond. You can see the pi bond has been homolytically cleaved. The other electron from the pi bond is now localized on that carbon, and there's a new radical formed. So there's a radical, not a radical, a closed shell species forms a new radical that is in fact an example of another propagation reaction. So we can see once initiation occurs, then a series of propagation reactions can occur. So it really does only require a trace amount of peroxides to get this going. So if there's just a little bit of peroxides in the ether solvent, then this reaction pathway can occur. Oftentimes it is undesired. And that's pretty annoying because you get a totally different constitutional isomer of the product that was desired. All right, now from this radical, it can keep reacting, and take a look at the product so we can see there's this CH bond in the product, and that can be generated in the following way. What type of step do you think that this is? Yes, this is another propagation step. All right, now this secondary alkyl halide, this closed shell, non-radical, it's formed. And that might be the desired product, but a new radical is also formed. That's the bromine radical. And you can imagine that it now, just like we saw here, reacts with another molecule of alkene and just keeps this whole cycle going. To recap, initiation generates the radical species. In the case of this reaction, initiation occurred when the oxygen-oxygen bond of the peroxide contaminant cleaved homolytically to generate alkoxy radicals. The alkoxy radicals could abstract a hydrogen from HBr. That is the name of this particular propagation step. Yes, they have names. I will try to spare you that. Following this propagation step, a new radical was formed. That new radical reacted with another closed shell species, aka another non-radical that happened to be a pi bond, to generate a new radical, aka propagation. That new radical reacted with yet another closed shell species, non-radical, and another hydrogen abstraction, just a type of propagation step, to generate a closed shell species and a new radical. So be sure you see the pattern. Initiation, no radical makes radicals. Propagation, one radical and a non-radical makes a new non-radical and a new radical. Wow, say that 5 times fast. The one step we did not show is termination. It's because termination is actually pretty rare. So if it's required that you show a termination step, you can do that. But typically when we are drawing these mechanisms, we don't show termination because it is rare. The most probable outcome actually is that a radical interacts with a closed shell species, just thinking about the fact that there are many, many more closed shell species, non-radicals than radicals in the solution. Okay, but termination, 2 radicals come together, those unpaired electrons come together and generate a closed shell species, one without unpaired electrons. There we go. That is an example of a termination reaction. 2 radicals, the bromine radicals, coming together to form a closed shell species. This is not a radical. Well, great, we just drew a mechanism. However, how can we understand the difference in regioselectivity, meaning the difference in which constitutional isomer of product is formed? For hydrohalogenation in the absence of peroxide contaminants, the hydrogen atom bonds to the less substituted carbon, carbon 2, and the bromine atom, as bromide, bonds to the more substituted carbon atom of the alkene, in this case carbon 3. This generates the tertiary alkyl bromide, the more substituted of the 2 possibilities, tertiary or secondary, which is referred to as the Markovnikov product. However, we just learned an exciting surprise, which is that in the presence of peroxides, the anti-Markovnikov product, the less substituted alkyl halide, is observed, where the hydrogen atom of HBr bonds to the more substituted carbon, carbon 3, and the bromine atom, this time as the bromine atom, bonds to the less substituted carbon, carbon 2. How can we understand this result? How can we explain it? Let's just take a time out and state a universal truth, which I have mentioned before. And that truth is that the observed pathway is the lowest energy pathway in both cases. And because different products were formed suggests that there were different pathways at work in the presence and absence of peroxides. In the absence of peroxides, just hydrohalogenation. This reaction proceeded via carbocations, and the most stable carbocation was formed. In the case of hydrohalogenation in the presence of peroxides, this proceeds via radical intermediates, and as you would guess, the lowest energy radical species will be formed. When I drew out the mechanism above, I did show this radical. How do we think about radical stability? Well, radicals are electron poor, just like carbocations. Carbon does not have a filled octet, and thus radical stability parallels carbocation stability. A tertiary radical is the most stable, lowest energy type of radical. Of course, delocalized would be even lower energy, but let's not worry about those that are described by resonance structures yet. Okay, then secondary, then primary, and the highest energy would be the methyl radical, just like for carbocations. So both of these processes proceeded via the lowest energy species. It's just that those species were different. The carbocation in the case of HBr addition in the absence of peroxides, and the radical in the presence of peroxides. So once we feel comfortable with this outline, once and for all, let's explain the differences in regioselectivity. So which constitutional isomer product was favored between these two reactions? For hydrohalogenation in the absence of peroxides, so occurring via two electron steps, two electron processes. The first and rate determining step is an electrophile addition step between the alkene starting material and HBr. Either carbon 3 or carbon 2 of the alkene can make the bond to the proton, which is E+, that is adding to the pi electrons. If carbon 3 bonds to the hydrogen atom, a secondary carbocation is formed. However, if carbon 2 bonds to the hydrogen atom, a tertiary carbocation is formed. The tertiary carbocation is lower energy than the secondary carbocation. And since this first elementary step is rate determining, the energy of the intermediate determines the energy of the activation barrier, the transition state for that first step. The tertiary cation will have a lower activation barrier than formation of the secondary cation. Thus, the tertiary carbocation is formed. It represents the lowest energy pathway, and it is the observed intermediate. The secondary carbocation is not observed. It is higher energy. And even though a coordination step could happen on that secondary carbocation to form the secondary alkyl halide, because the secondary carbocation is not formed, the secondary alkyl halide is also not formed, not observed. The more stable, lower energy tertiary carbocation leads to the observed product, where the hydrogen atom has made a bond to the less substituted carbon, carbon 2, because that generates the more substituted carbocation, and then bromide makes a bond to that more substituted carbon, leading to what is referred to as the Markovnikov product, the more substituted alkyl halide. If you're having trouble understanding what I mean by the more substituted product, please do look at the carbon bonding to bromine. For the reaction in the absence of peroxides, bromine bonds to a tertiary carbon, making a tertiary or more substituted alkyl halide. In the presence of hydrogen peroxide, a secondary alkyl halide is formed. So the less substituted alkyl halide is formed in the presence of peroxides. Speaking of in the presence of hydrogen peroxide, let's take a closer look at the radical mechanism. As we discussed, in this process, first initiation must happen where the oxygen-oxygen bond of peroxide is cleaved to generate alkoxy radicals. Those alkoxy radicals propagate the radical by reacting with HBr to generate the bromine radical. Now, the bromine radical can react with the pi electrons of the alkene. So just take a moment here to think about in contrast to the reaction in the absence of HBr. It's hydrogen that makes a bond first to the two carbons of the alkene. In the radical reaction, it's bromine. Bromine can either bond to C3 to generate the secondary radical or C2 to generate the tertiary radical. Just like in the case of the reaction via carbocations, hydrogen could have bonded to C3 to make the secondary cation or C2 to make the tertiary cation. In both cases, the pathway that occurs is the one where the atom, either a hydrogen or bromine, makes a bond to C2, because that leads to either the tertiary cation or the tertiary radical. Both of these are electron poor intermediates, so they are most stable when either the cation or the radical species is the most substituted, or the charge or the radical is localized on the tertiary carbon rather than the secondary carbon, which is the alternative. So in the case of the radical reaction, bromine bonds first, generating this radical species. And as we've said, we do not expect the secondary radical to be formed as long as this is the rate determining step. And I do need to say that the energetics of radical reactions are complicated, and I'm not going to go into all of that here. But just based on the principles of radical stability, we do expect the tertiary radical to be favored. And so since the secondary radical is not expected to be formed, then neither is the product resulting from the secondary radical, which would be the tertiary alkyl halide. However, the more stable tertiary radical does continue on this propagation pathway, reacting with HBr to generate the secondary alkyl bromide. So one more time, in both cases, the reaction does proceed via the lowest energy pathway. It's just that the pathways are different. With this summary in mind, let's revisit the warm-up questions from the beginning of the lesson. Here they are. Think about your answers. Revise your answers if you'd like. If you did not try the problems, try them now. For each of the four reactions an alkene is reacting, it's an asymmetric alkene, or the two carbons have different substitution patterns. However, in each case, it looks like two atoms have added across the two carbons of the alkene. For reaction A, this is a hydration reaction where water, HOH, has added across the two carbons of the alkene. It does appear that this product does come via the more stable of the two possible carbocations that could potentially be formed in this reaction. So this reaction is just a acid catalyzed hydration. As those reactions do proceed via the more stable carbocation, in this case secondary versus primary, to generate the more stable of the two possible alcohol products. The second reaction, however, has the product which would be the result of the less stable carbocation reacting. Now, that less stable cation cannot be accessed. However, a different reaction pathway can be used to generate the less substituted alcohol product, as we learned in Organic Chemistry 1, and that is hydroboration oxidation. Both of these reactions occur under two electron processes. There are heterolytic bond cleavages and bond formations. However, this reaction proceeds via a different mechanism, and so the less substituted product can be formed. Okay, these two are just reviews of Organic Chemistry 1 to get you warmed up for what to think about with hydrohalogenation. The next two reactions do involve HX-HBr addition across the two carbons of the alkene. We can see in reaction C, this product reminds us of the product of reaction A, and that it would have been formed via the more stable secondary carbocation. Thus, this reaction C is just a straight up hydrohalogenation, just as you learned it in Organic Chemistry 1. However, the product of reaction D is the less substituted alkyl halide, And one thing we know for sure is that it did not come via the primary carbocation. This would immediately rearrange to that one, even if it was formed, and then it is higher energy. The primary cation is higher energy and is not formed in this reaction. So a different mechanism is needed, or a different synthetic pathway. So in fact, if peroxides are added to the reaction mixture, it only requires a trace or catalytic amount. The less substituted alkyl halide is observed. Doesn't go via a secondary cation, it goes via a secondary radical. And bromine bonds to the primary carbon because bromine bonds first, as we discussed at length in the past several minutes. And these are the most stable intermediates in those two reaction pathways. The pathways are just different. Now I will just point out that if you remembered hydroboration, you might have been able to propose a lengthier route to this desired less substituted alkyl halide. You could do that via the alcohol. So first treat under hydroboration conditions, and then with PBr3 to generate the alkyl bromide. Okay, so you already knew a route to this, just through a multi-step process to the less substituted alkyl halide, but now you know a one-step method and you've learned something about radical chemistry. So let's continue learning about radical reactions. Pause and propose a complete curved air mechanism to explain this transformation. Once you've given it a try, let's discuss. An initial analysis suggests a substitution reaction where hydrogen is substituted for bromine. The only time we've seen something like that happen is with electrophilic aromatic substitution. Hydrogen is not a leaving group, so this is confusing, perhaps initially. We might also notice that this substitution is occurring at a benzylic carbon. And we have discussed the benzylic carbon before. We have recalled that benzylic cations are more stable than similarly substituted cations because there are several resonance structures that we can draw that demonstrate that the charge is delocalized into the ring. So this represents a conjugated system and can be formed when the benzylic carbon is sp2 hybridized. Right, just a p orbital that is aligned with the p orbitals of the ring is required for this conjugation. Our attention may be drawn to the light in this reaction, the light as a reagent. Light, as we know, excites electrons, or at least light with the proper wavelength corresponding to energetic changes. Allowed energetic changes for the electrons can excite electrons. In this diagram, I've shown how light can convert a ground state, pretend molecule, to the excited state. Taking a look at the excited state, what does it look like? Yes, a radical. So light can excite electrons to make radicals. And in the case of this reaction, it excites electrons in the bromine molecule to generate bromine radicals. The first step of this reaction is an initiation, as is the case with all radical reactions. One of these bromine radicals can react with one of the CH bonds from the benzylic position of this alkyl benzene, generating a new radical in a close shell species, a non-radical, making this a propagation step. Now this is a benzylic radical. The radical is on the benzylic carbon, and thus can be described by resonance structures. Get ready for this, everyone. So let's draw the resonance structures that show the delocalization of the radical into the ring. All right, let's show another. Resonance structures with single electrons are fun, huh? Yeah, I don't really mean that. All right, these resonance structures do demonstrate that the radical is delocalized. And this makes for a lower energy radical, as we have previously learned about conjugation. This benzylic radical continues to react, and it does so in another propagation step with bromine. to generate the alkyl bromide and another bromine radical, which of course can re-enter the cycle and continue to react. To summarize, in the presence of light and molecular bromine, a benzylic hydrogen can be substituted for a bromide. In fact, these CH bonds at benzylic carbons are especially susceptible to radical or homolytic dissociation, homolytic bond cleavage. Bromine is not the only molecule that reacts with alkylbenzenes in this fashion. So how can we understand this? Why is the benzylic CH bond especially susceptible to radical homolytic bond cleavage? Homolytic bond cleavage of that CH bond would generate this benzylic radical. Now, if you did not take the time to draw the resonance structures on the previous slide, pause now and try to draw those resonance structures on your own. I've redrawn those resonance structures here and reminded you that this delocalized or conjugated radical is lower energy than those that are not conjugated, so localized radicals. And thus, the benzylic CH bond can undergo a substitution reaction with bromine via this radical pathway. Not only can the benzylic position react this way, so can and so does the allylic position. So here's an example of an allylic bromination. Before I read the slide, let's just map out what's happening here. The first reaction shows a benzylic bromination. The second reaction shows an allylic bromination, and both reactions involve a reagent that we have not learned yet. This new reagent is abbreviated NBS. It stands for N-bromosuccinimide, and it is an alternative to bromine for generating the bromine radical. So this N-bromine bond, NBr bond, it is labile, meaning it is susceptible to homolytic cleavage. So it can cleave, and that will generate these two radical species. And as before, this bond cleavage is facilitated by light. If you are wondering, why would one use NBS? Well, it's an alternative to bromine. Again, that doesn't answer the question, but remember that bromine is a corrosive liquid, which is one reason to avoid it. Also, what have you previously learned that bromine will react with alkenes? Yeah, we've learned that it'll make these dibromides. So bromine in the dark, so with no light, unconcentrated, will favor just formation of the vicinal dihalide. Low concentrations of bromine, so dilute, in the presence of light, can favor the allylic bromination. So to avoid any of this, so to avoid undesired reactivity of the alkene rather than desired allylic bromination, NBS can be used instead. If you're wondering about the mechanisms of these reactions, they are similar to the benzylic bromination with bromine in the presence of light, except that the radicals are generated by NBS. In the case of allylic bromination, the allyl radical is delocalized, just like the benzylic radical was, and we showed that on the previous slide, so I did not redraw out the resonance structures here. Let's pause and add reactions to our reaction chart. First, the radical hydrohalogenation of alkenes. Hydrohalogenation suggests adding HX across the two carbons of an alkene. And that is indeed what happens in this transformation. However, the constitutional isomer of the product of the alkyl halide that is formed is different than the constitutional isomer that would be expected if just HX was used as a reagent. If just HX is used, X is expected to add to the more substituted carbon and H to the less substituted carbon. However, when trace peroxides are present, either on purpose or on accident, the selectivity is switched. The hydrogen atom adds to the more substituted carbon and the halogen to the less substituted carbon. But remember, This reaction still follows the laws of the universe. It does proceed via the most stable, more substituted radical. Radical hydrohalogenation of alkenes, check. Benzylic bromination. In benzylic bromination, an alkyl benzene with at least one benzylic hydrogen, we're calling that this is the benzylic position adjacent to the ring, can be treated with bromine in the presence of light to yield a net substitution product, but of course this is by a radical mechanism, not any of the substitution mechanisms that we have previously learned, that is for sure. The benzyl bromide is formed via a benzyl radical that is stabilized by delocalization of the unpaired electron. We can note here that NBS can also be used. And NBS is often used with the solvent carbon tetrachloride. So I apologize, I do not believe I included that on the previous slide. But be sure that you know that carbon tetrachloride is a common solvent for radical reactions. And the reason is it doesn't have any reactive CH bonds. Allylic bromination is quite similar to benzylic bromination in that it proceeds via an allyl radical that is stabilized by delocalization of the radical. The allylic position, an allylic CH, can undergo substitution to form an allyl bromide. Now, I've highlighted two different allylic positions. They are the same. There is a plane of symmetry through this molecule. So either of them can react, either of them do react. This one may react again to make a dibromide if you leave it in there too long, if you leave your reaction going for too long. But it is possible to be a careful chemist and just brominate one allylic carbon. So the preferred reagent for this is NBS. And again, carbon tetrachloride is the common solvent used for this transformation because it is inert. It does not contain any reactive CH bonds. I've drawn out the delocalized radical species that is an intermediate in this transformation. We can also note that this transformation can be achieved with bromine in the presence of light. And then I wrote that dilute in front of the reagents. That's because, as we have previously learned, when alkenes are treated with bromine, and usually this is more concentrated in bromine, and if you would like to avoid radical reactions, then perform it in the dark, so in the absence of light, those conditions will yield a product that you should be quite familiar with, which is the vicinal dibromide from just electrophile addition to the carbons of the alkene. Okay, so to avoid any of this confusion, any of this messiness, just use NBS for allylic bromination. Excellent. 4 more reactions to learn. Now that we know the basics of radical mechanisms, these will go a little bit faster, don't worry. Next up, halogenation of alkanes. Take a moment, pause, and predict the outcome of each of the following reactions. And if you think no reaction occurs, then please write no reaction. You may have predicted that an alkane plus molecular bromine yields borine, no reaction. I agree. Well, how do I know this? Well, because we've looked at, say, alkenes reacting with bromine, and the alkane part did not react up until 5 minutes ago, where we saw allylic bromination in the presence of light, but not with just molecular bromine itself. Plus that, hydrocarbons are solvents. Been using bromine all year with hydrocarbon solvents possibly, and there's been no reaction. So no reaction is what we predict for the treatment of this alkane with molecular bromine. However, as we have been noticing, in the presence of light, radicals can be generated, and then perhaps some reaction does take place. That is the case. The observed product of this transformation is this tertiary alkyl halide. And as you may suspect, that tertiary alkyl bromide was formed from this tertiary radical. We have discussed that radicals follow carbocation stability trends, and tertiary radicals are the most stable between tertiary, secondary, primary, and methyl radicals. So not considering delocalization of charge. All right, what? How did this happen? Well, it obviously involves light. So as we have learned, in the presence of light, the bromine-bromine bond is cleaved and generates two bromine radicals. This is the initiation step for this radical reaction. No radicals, radicals, initiation. Now, I have mentioned that one common pathway by which radicals react is to bond with hydrogen to abstract a hydrogen atom. And we can take a moment and think about all the different types of hydrogen atoms in this molecule. And I've just drawn a few here. This hydrogen atom is bonded to a tertiary carbon, this hydrogen to a secondary carbon, and this hydrogen to a primary carbon. Abstraction of the hydrogen bonded to the tertiary carbon will yield a tertiary radical, which we do know is more stable than a secondary or primary radical. So in fact, that is the major pathway observed here. And even if we don't know that, we do know that we expect it to be. Okay, this is the propagation step. Closed shell species, radical makes a new radical in a closed shell species. Propagation. We're going to call this propagation number 1. In propagation step number 2, the tertiary radical that was formed in the first elementary step reacts again, this time with molecular bromine, to generate the tertiary alkyl halide and another bromine radical which can re-enter the cycle. To summarize, when an alkane is treated with molecular bromine in the presence of light, which generates radicals, a tertiary, in this case, alkyl bromide is observed. And the way we're understanding that is because in the first propagation step, there were several different types of hydrogen. So there's secondary hydrogens, and there's other ones I didn't label here. There's hydrogens bonded to tertiary carbons and hydrogens bonded to primary carbons. And of those hydrogens, it seems as if bromine, the bromine radical, abstracted the hydrogen atom, in this case, the one bonded to the tertiary carbon, and generated the most stable of the possible radicals that could be formed. Abstraction of the secondary hydrogen would have made a secondary radical. Abstraction of the hydrogen bonded to the primary carbon would have made a primary radical. All right. Now, one question you might have is that we have been discussing bromine a lot today. Do these radical reactions occur with any other halogens? Well, let's transition to thinking about that. Take a moment and predict the products of these reactions. Under these conditions, X2 and light, a radical halogenation occurs of the alkane. For this particular alkane, there are 4 different types of hydrogens. So 4 different types of hydrogens in this molecule. And halogenation at each of these types of hydrogen could generate 4 unique products. Now, for the bromination reaction, there is a clear major product observed. What do you think it is? What is your prediction? Yes, it's the tertiary alkyl halide. It's the tertiary bromide. This is the major product of bromination. We would expect this because it would proceed via a tertiary radical species. Now, you might be a bit surprised to know, however, that the result of reaction with chlorine is actually a mixture of constitutional isomers. What? What? That doesn't make any sense. You said it would go through the tertiary radical. I said we would expect it to go through the tertiary radical. I also said that the kinetics of radical reactions are complicated, and that is the case. So if you'd like to know what's going on here, then tune in. If you'd prefer to not know, then tune out while I'm on this slide. Recall the 2 propagation steps in the halogenation reaction. In propagation step 1, the halogen radical reacts with one of the CH bonds to form a radical and HX. In propagation step 2, the radical that was formed in propagation step 1 reacts with molecular halogen to form the final product. It is propagation step 1 wherein the explanation to this observation lies. That again, that bromination is selective for the more stable radical species, and that chlorination is not. And there's two key points. The first is that the chlorine radical is higher energy than the bromine radical. So you see I've put the chlorine radical plus the alkane a little higher energy than the bromine radical plus the alkane. And yes, I'm using a different alkane for simplicity's sake. I'm using propane. The second important point is that the HCl bond that is formed in propagation step 1 is stronger than the HBr bond that would be formed in propagation step 1. Thus, since chlorine starts out higher energy than bromine, and because the HCl bond is lower energy than the HBr bond, propagation step 1 is exothermic for chlorination and endothermic for bromination. All right, make sure you have that part. Now, it's important to apply a fundamental postulate of kinetics, which is the Hammond postulate. The Hammond postulate states that for endothermic elementary steps, the energy of the transition state depends on the energies of the products of that step. So the transition state looks like the products of that step. For exothermic steps, however, the transition state is closer in energy to the reactants of that step, and so it looks more like the reactants. So the products of that step don't really determine the energy of the transition state very much. So because of that, because for chlorination, the green curve, this is an exothermic step. Radical stability doesn't really affect the transition state very much. And because of that, both radicals are formed, both products are formed, and the reaction isn't very selective. Because bromination is an endothermic step, the transition state looks like the radical, and so radical stability does affect it. The more stable radical is formed, and so only the product resulting from the more, not only, but the product resulting from the more stable radical is the major product. So for example, in bromination, about 96% of the product mixture is the secondary bromide and 4% is the primary. For chlorination, it's more of a 60-40 mixture. Cool. I hope that helped. If it didn't, ask me questions if it didn't, if you care. If you really don't care, I'm not going to tell you that you have to understand and know this because you don't. What you have to know is that bromination is selective, chlorination is not. If you know why, that's great. It makes me so happy, but you don't ultimately have to. And if you were to think about, oh, why would you ever do this reaction? Why would you halogenate an alkane? Well, it's because you could take it on and do something with it. For example, looking back up at our reaction chart here for allylic bromination, so just taking a look at the allylic bromination products, this reaction is pretty commonly used in order to generate dienes. So now imagine treating this with potassium T-butoxide, that's E2 conditions. That would generate a diene, which could then undergo Diels autoreactions. Cool. That's one of the main reasons why we're learning these reactions, because they're synthetically useful. And that's especially in the case of alkanes, right? Alkanes, I mean, we don't know really any reactions of them. However, now we know that we can treat an alkane with bromine in the presence of light and perform a substitution reaction for the most substituted carbon-hydrogen bond because it goes via the most stable substituted radical. We also know we're going to avoid chlorination. Yikes, we don't like mixtures. We have to separate them. We'll add this to the reaction chart. When an alkane is treated with molecular bromine in the presence of light, substitution of the most substituted carbon-hydrogen bond for a halogen will occur. We know that this reaction will also occur with chlorine, but as we said, a mixture of isomers is formed, so we'll typically avoid it. Unless only one isomer is possible, then perhaps you could imagine also using the chlorination reaction. So let's add it. And for this particular example, there are two types of hydrogens, and so two products will be formed. But you can imagine that instead of propane, we treated cyclohexane with chlorine under these conditions. There's only one type of hydrogen, and so only one type of product will be observed. Only one constitutional isomer product is possible. So in this case, it is useful. So perhaps I was a little hasty to say avoid. Let's say avoid chlorination of alkanes in favor of bromination when multiple isomers are possible. All right, moving right along. 3 more reactions: dissolving metal reduction, Birch reduction, and Ott oxidation. These are all very exciting reactions. Let's get to it. We will begin with a review. So provide the reagents necessary to accomplish each of the following transformations. Right here. Last chance. Alkyne to alkene, 2 equivalents of H2, and I mean 1 equivalent. 2 equivalents have been added across the 2 carbons of the alkyne. This represents a hydrogenation reaction, a full hydrogenation reaction with hydrogen gas in the presence of a palladium on carbon catalyst. The first equivalent of hydrogen is added in a syn fashion, generating this cis-alkene intermediate. But recall that the cis-alkene intermediate is even more reactive than the alkyne. So it continues to undergo hydrogenation until the alkane is formed. But no, the cis-alkene was the desired product. Too bad. The reaction cannot be stopped here. However, we do know how to stop the hydrogenation at the cis-alkene. This involves a less reactive catalyst. We call it a poisoned catalyst. Still, hydrogen gas is necessary, but just one equivalent is desired this time. So a less reactive catalyst is used. It's still palladium on carbon, but it involves a poison. So it's with a poison, and that catalyst has a name. The name is Lindlar's catalyst. And just to remind you, Lindlar's catalyst is just simply palladium on carbon with a poison. Now, poison just means something that bonds to the catalyst and makes it less reactive with the alkene. Commonly, that poison is quinoline. What about the transalkene? Is there some way to directly convert the alkyne to the transalkene? So to just add one equivalent of H2, but in a trans fashion? Well, not by hydrogenation, because by hydrogenation, the hydrogen atoms are added syn. They add to the same face of the alkene at the same time. So they are syn. It's a syn addition. All right, well, how will we do this? I've asked this question before, and clever students have given me very good answers. Students have suggested before hydrogenation with Lindlar's catalyst to generate the cis-alkene. Then from the cis-alkene, let's just move all the way to the side. From the cis-alkene, add HBr or HX. Okay, so now we have this species. And then eliminate. Okay, in E2 elimination with a strong base such as sodium methoxide, sodium hydroxide, sodium T-butoxide, so E2 elimination. You could also imagine that you could perform an acid catalyzed hydration instead to make an alcohol, then do an E1 with sulfuric acid. Either way would make sense. The transalkene is expected to be favored here because this is the more stable isomer. Transalkenes are more stable than cis-alkenes. I've also had very clever students who quickly integrate information into their brains more quickly than me. Recall that the alkane could be brominated. These are benzylic positions, right? This is a benzylic position. Both of these are. So a benzylic bromination could be done to generate this alkyl bromide. And then this alkyl bromide could be treated with a base. Just as we said before, sodium methoxide, sodium T-butoxide, sodium hydroxide, and its conjugate acid. Any of those bases would work for D2. Okay, many options here to make this transalkane. I thought that was a 1, 2, 3-step process. Maybe we can learn a 1-step process that proceeds via radical conditions. Let me share with you a very interesting reaction, and that's called the dissolving metal reduction. It essentially performs an anti-hydrogenation of alkynes. And it's really just an anti-addition of H2. Okay, so alkynes can be converted directly to transalkenes under these amazing, awesome, interesting reaction conditions. The alkyne is treated with sodium metal. So this is solid sodium metal, that soft silvery metal. Sometimes you see it written like this. That 0 lets us know that it is the metal. It is not the cation. And then in a liquid ammonia solvent. Serious stuff. But ammonia is usually a gas, you say. Yes, this is run at very low temperatures, temperatures at which ammonia is a liquid. Those low temperatures are maintained by conducting the reaction with the flask in a dry ice acetone bath. Okay, where acetone is the organic solvent, dry ice, obviously solid CO2. So that very cold bath maintains those low temperatures necessary for this reaction to occur. What is that blue color about? Let's find out. So we will use a complete curved Durham mechanism to explain how transalkene is formed via the dissolving metal reduction. And that metal, sodium, does dissolve in liquid ammonia. Although I suppose it's a bit more complicated than that, because not only does it dissolve, it ionizes. And it makes a solvated sodium cation and a dissolved electron. I know, it's so cool. And this is just indicating that these species are dissolved in ammonia. If they were dissolved in water, it would say AQ. And this solvated electron is responsible for that brilliant blue color of the reaction mixture, which we saw here. Very nice, right? So that blue color is because of the solvated electron. And yes, I took this from the internet. Credit, credit, credit. All right. I saw this reaction in real life one time, and it was really a beautiful reaction. Okay, so now the alkyne can react with that electron. This is sort of an initiation. There is a radical, there is a dissolved electron in solution here. So that electron will react with the pi bond, pair up with one of the electrons from the pi bond, and generate now a radical anion. And I'm going to abbreviate the rings as phenyl for simplicity's sake, kind of because I'm feeling lazy. So this radical anion is currently in the cis conformation. And I know it looks like a pi bond. There's no rotation around that bond. Well, for the radical anion, there is. So bond rotation can occur about this bond and relieves the steric interaction between those two phenyl groups. The more stable trans radical anion is formed. The trans radical anion goes on to react with the ammonia solvent in a proton transfer reaction, resulting in this radical intermediate. This radical intermediate has this unpaired electron, which can pair up with another dissolved electron in solution. This termination step of sorts generates an anion that will act as a base, accepting a proton from the ammonia solvent, generating the final transalkane product. There's the proton that's added in that step. Here is the proton that already existed. All right. The keys to understanding this reaction are simply that the transalkene is more stable than the cisalkene. due to steric interactions in the cis alkene. And free rotation is possible at the radical anion stage. Just a quick note, you would not use this reaction with terminal alkynes. Well, there's no cis or trans in terminal alkynes, but sometimes reduction of them is desired. But you would not use dissolving metal reduction because we can see that an equivalent of amide, actually two equivalents of amide, are generated in this process, right? One equivalent here, and then another equivalent that I did not draw at this proton transfer step. So those equivalents of amide, they will react with the terminal alkyne. Terminal alkynes have a pKa of 24, whereas the ammonia has a pKa of 35, which is just to say that once the amide is formed, it will react with any unreacted terminal alkyne. So do not use dissolving metal reductions with terminal alkynes. You would just use instead, if you desired to stop at the alkene, you would just use instead hydrogen gas and Lindlar's catalyst, the poison catalyst. All right, very good. Now you know how to generate transalkynes in one step. It's with the dissolving metal reduction. And we can add that to the chart here. For dissolving metal reductions, an internal alkynes, or both carbons of the alkyne are bonded to alkyl groups, can be treated with sodium metal in a liquid ammonia solvent at low temperatures to generate transalkenes. And just be sure that you understand that this provides a route to transalkenes from alkynes that was not previously available to you. Previously, the only hydrogenation reactions you knew of alkynes made cisalkenes or alkanes. And now you know a direct way to generate the transalkene from an alkyne. Awesome. Two more to go. Birch reduction, autooxidation. Let's get it. So to introduce the Birch reduction, please propose reagents to accomplish each of these transformations. Alkene to alkane, easy peasy. Hydrogen gas with palladium on carbon catalyst. Again, that is a syn addition of H2 across the two carbons of the alkene. If stereocenters were generated, we would expect a single diastereomer, where the hydrogen atoms added to the same face. To convert an alkyl halide to an alkane, the most straightforward way would be via the alkene shown in the previous scheme. So E2 elimination with a strong base, such as potassium T-butoxide in the presence of its conjugate acid, T-butanol as the solvent, will generate this alkene, followed by hydrogenation would generate the alkane shown. You could imagine different routes to make the Grignard and then treat it with water. But this would be the most straightforward. All right, what about this molecule where the cyclohexene or cyclohexane is now a benzene? How can this be fully reduced to form this molecule? It looks like 3 equivalents of hydrogen gas have been added. You may be saying this cannot be done. Well, it can. It can be done with hydrogen gas, but it's going to require a little bit different conditions. So instead of palladium on carbon, a nickel catalyst at 135 degrees Celsius and 160 atmospheres of hydrogen gas. Say what? 160 atmospheres of hydrogen gas. Yes, I didn't. That is correct. I did not misspeak. So I would call these forcing conditions. At this point, we all understand why forcing conditions are necessary. This product is non-aromatic. The Birch reduction is related to the dissolving metal reduction, and it's a way to reduce benzene. So it does not require 160 atmospheres of hydrogen gas. It does, however, require solid lithium metal. And T-butanol is an additive here. It's not the solvent. It is serving as a proton source. We saw in the dissolving metal reduction of alkynes that the liquid ammonia served as a proton source. That is not the case. The T-butanol additive is necessary. But the liquid ammonia is the solvent here, and obviously this is occurring at low temperatures. Otherwise, ammonia would not be a liquid. And that's not the only reason why low temperatures are used, but that is certainly one of the reasons. Typically, low temperatures are used when reactions are exothermic or when at higher temperatures, the reaction will form a mixture of products. Okay, so an aromatic molecule is converted into a non-aromatic molecule. How does that happen? You can go ahead and propose a mechanism on your own. After learning the dissolving metal reduction, you're pretty well equipped to propose a mechanism on your own. The pi electrons of benzene react with a dissolved electron that comes from lithium. And that way, this reaction is very similar to the dissolving metal reduction. A radical anion is formed, which is basic as you would expect, and so it reacts with the alcohol additive in a proton transfer reaction to generate a radical species. This radical reacts with another dissolved electron in solution to generate an anionic species. This anionic species can be described by two other resonance structures. Try to draw them on your own. However, the major resonance structure for this species is this one, and whether or not you would have predicted that, I am letting you know that that is the case. As you might expect, this species is basic and can react with that T-butanol additive. This time I'll draw out the Lewis structure of T-butanol just for fun. Proton transfer reaction occurs to generate this non-aromatic product. First, you will notice that this non-aromatic product is a 1,4-cyclohexadiene. Those two double bonds are isolated. And we know that if this encounters a trace of acid, for example, it will isomerize to form the more stable 1,3-diene. Okay, that's not part of this problem. We're just remembering the properties of 1,4-cyclohexadienes or 1,4-dienes. Good. This is, again, similar to dissolving metal reduction. So predict the products of each of these reactions. For both of these reduction reactions, two constitutional isomers of product are possible. When the substituent on the benzene is an electron donating group, the electron donating group is on one of the carbons of the 1,4-diene. We'll just call it carbon 1, but it could have easily been carbon 5. When the group on the benzene ring is an electron withdrawing group, such as nitro, that substituent is between the alkenes. And this can be understood by resonance structures of the anionic intermediate. But I'm going to spare you that for today. So electron donating groups on the benzene ring favor this isomer product. Electron withdrawing groups, this one. Live it, learn it, love it. Did that help us? I mean, kinda. We can convert now alkyl benzenes into dienes, which is exciting. As far as facilitating this transformation, it can be conducted again with 160 atmospheres. And it's just a ridiculous pressure of hydrogen gas with a nickel catalyst at elevated temperatures. This will be one of the most unsafe reactions you have ever run. With the Birch reduction, we can make it slightly more safe. We are using lithium metal, but we will be careful. Lithium metal, T-butanol additive as the proton source, ammonia solvent at low temperatures. This is the Birch reduction, which will yield, as we said, a 1,4-diene, which can be hydrogenated to the final product under normal hydrogenation conditions, just the hydrogenation conditions for alkenes to alkanes that we looked at right here. And I promise I do these review questions for a reason. And we can add that to our reaction chart. I mean, I think we just did that, but I will quickly write it up for you. All right, here we go. One last reaction to tackle here, and that is autooxidation. So back to that butter question. So, what happened to that butter I left on the counter and tasted so bad? Did you think that I was losing it when I brought up butter earlier? Well, I could be losing it. However, I would like to introduce you to a really important radical reaction. Now, alkenes in the presence of oxygen gas can react to form peroxides. This is extremely annoying because this is not usually a desired reaction pathway. This is one reason why organic compounds are often stored outside of the presence of oxygen. Okay, and aldehydes as well, they can react with oxygen to undergo oxidation to carboxylic acids. Oxidation of these functional groups just in air is referred to as autooxidation. All right, what happened to that butter? Well, as many of you know, fats have the following structure. There's this glycerol backbone derived from glycerol, and their fats are esters. So there's been an esterification between some fatty acid, which has a bunch of carbon atoms. Leave it at that. So some fatty acids and glycerol, alcohol, acid, form an ester. And these fatty acids that make up these triglycerides, these fats, they can have all single bonds. There can be double bonds. There's a wide variety. When there are fatty acids that have double bonds, these are referred to as unsaturated. So here's an example of some triglycerides, some fat that has an unsaturated fatty acid as part of it. And this unsaturated fatty acid that happens to be in butter sat out on my counter in air, which contains oxygen. What do you think happened? Yes, look at these allylic positions. The culprit is the unsaturated acid. Those saturated parts, they are pretty boring, but the unsaturated part has allylic CH bonds. What have we said about allylic CH bonds? They are labile, just like benzylic, aka they are prone to homolytic cleavage. What is oxygen? Oxygen is a diradical. We're all terrified now, right? Oxygen is a diradical. No initiation needed. This radical exists. And what can happen here is the following. One of these allylic hydrogens can react with oxygen from the atmosphere to form a delocalized allylic radical. You can draw the resonance structure. I am tired. Such a long video. You're like, I'm not tired? Yes, I know you're tired too. So delocalized allylic radical. And that delocalized allylic radical can undergo a termination reaction to form this oxidized product. Let's see how small I can make this. Well, it turns out I can make it pretty small. So it can undergo termination and generate this species. And these species taste horrible. The formation of peroxides like this are responsible for fats becoming rancid, going bad, tasting bad. So there you go. Who knew that radical chemistry was responsible for the decomposition, for fats tasting bad? Okay, we're going to end. Don't worry. However, if you want to leave butter on the counter, if you like soft butter, just leave your salted butter on the counter. The salts slow down this process from happening. Cool. All right. Now, summarize. What have you learned today? What questions do you have? Please let me know. Revisit your learning goals. So we should be able to draw the complete curved error mechanisms for reactions that proceed via radical pathways. We have learned a couple of those reactions. We've learned how alkenes are converted to the anti-Markovnikov alkyl halide. So radical hydrohalogenation. Benzylic bromination with both bromine and NBS. Here we go, NBS. Allylic bromination with either bromine or NBS. It goes by the same mechanism. Okay, those are the first three on the list. We also learned the mechanism for halogenation of alkane. So alkane to alkyl bromide. Okay, that's the first four on the list. We learned the dissolving metal reduction reaction to generate a transalkene from an alkyne. The Birch reduction, benzene was reduced to a 1,4-cyclohexadiene. We learned about substituent effects. And finally, super exciting, Ott oxidation, just the radical oxidation of alkenes at the allylic position, or even aldehydes at the aldehyde carbon, the carbonyl carbon, to generate whatever this is in carboxylic acids. And we learned that this process is responsible for fats going bad. All right, I hope you had fun. I had a lot of fun. It was totally radical. Do these practice questions, please, please. And after that, do even more practice questions.